Now, you may also know from previous experience that we can have multiple bonds in structures between elements. We can have double or triple bonds. What does that look like, and why would we do something like that? Well, multiple bonds are formed to ensure that each of the atoms has 8 electrons around it, has 8 valence electrons. Basically, multiple bonds, we only use them in order to ensure that each element follows the octet rule, providing it's not one of the exceptions. So in this particular, in a few examples here, I'll try to illustrate that. If we take O2, oxygen in the air, for example, and if we first take its 2 Lewis structures here, and we see each oxygen atom has 2 valence sites. If we simply pair up one of those sites, as we've done before, to form a shared pair of electrons to form a single bond, what we'll notice is that each element still only has 7 valence electrons around it rather than 8. So 2, 4, 5, and then 2 from the shared pair, that gets you to 7, and the same for this other oxygen. And we haven't, neither element has followed the octet rule. So how we remedy that situation is essentially taking 1 electron from each element and bringing them together to form a second shared pair. And so now we have actually 2 pairs of electrons that are shared between the 2 elements. And we can represent each pair of electrons with a line, so now we have a double line or a double bond between the 2 elements. Now, because each line represents 2 electrons, each oxygen atom has a total of 8 valence electrons around it, and both are then satisfying the octet rule. A couple other examples I'll show here. CO2, we can again look at the Lewis structures, and you can see the Lewis structure for oxygen is drawn a little bit differently here, but if we take these and just simply pair them up, what we'll notice at first, if we simply pair 1 site on each, that each of the oxygens will have only 7 valence electrons around them. Carbon will only have 6. And then if we take one electron from each element to form an additional bond, then we'll find we're sharing 2 electron pairs on each side of the carbon. So carbon is sharing 2 electron pairs with the oxygen on the left and 2 electron pairs with the oxygen on the right. So it ends up having 2 double bonds attached to it in this case. We can also do triple bonds. So N2 is a good example. You can pair the first set up, but that would only give you 6 valence electrons around the 2 elements. Bringing 1 more electron in from each gets you closer, gets you up to 7 shared, but then bringing 1 more gets you to 3 shared electron pairs, but each nitrogen now has 8 valence electrons around it. The 3 electron pairs, each of them are represented by a line that are shared, and so we end up with a triple bond. Now, all of this might be a little bit confusing. You might be a little bit concerned, how exactly am I going to make multiple bonds by bringing in electrons from one element and the other one, and how do I know which way I go? And all that could be slightly confusing. And it turns out there's some cases where you simply drawing and pairing up the valence sites won't work fully to give you the correct structure for the molecule. And so there is one uniform system for writing Lewis structures that should work in every case. And so from here on, I'll recommend this, this kind of format for writing Lewis structures, these rules to abide by. So the very first thing that we do, the first rule is that we write the total number of valence electrons, and we factor in any charge. So, and when I say the total number of valence electrons, I mean the sum of all of the valence electrons of all of the atoms in the molecule, and adding or subtracting any electrons for the charge. If I have a negative charge, I add a number of electrons equal to that charge. If I have a positive charge, I subtract electrons equal to the magnitude of the charge. The next step is that I place the atom that has the greatest valence, so the greatest number of unpaired electrons. I'll take that atom and place it in the middle, and then connect the other atoms to that just using single bonds. Now, if there is a tie for elements with the greatest valence, for example, if we have something like SO2, sulfur has 6 valence electrons, has 2 valence sites. Oxygen has 6 valence electrons, but has 2 valence sites. So neither of them, they each have a valence of 2, neither one has a greater valence. But sulfur is lower in the periodic table, so we will place that one in the middle and place the oxygens around it in that example. Then we add lone pairs to the outer atoms first to complete the octet around each of the outer atoms. And then any remaining electrons we would place around the central atom. Once we've done all of that, we evaluate and simply say, okay, have we satisfied the octet rule for all of the atoms? And if we have not, then we need to make multiple bonds as necessary to complete the octet around all of the atoms, with of course the exception of hydrogen or other elements that don't prefer 8 electrons around them. But in the vast majority of cases, we will complete the octet around all atoms. Let's go through an example of what this would look like. The carbonate ion, CO3 2-. The very first step is write the total number of valence electrons factoring in any charge. Well, if I look at carbon, I know that it has 4 valence electrons. Oxygen has 6, and I've got 3 oxygens, so I have 18 valence electrons coming from oxygen. I also have a charge that I have to factor in. It's a minus charge, so I have more electrons. I have additional electrons, so 2- means that I have 2 valence electrons just coming from the charge. I have 2 extra electrons, thus giving me the -2 charge. So if I sum all of this up, I come out with 24 valence electrons. And I've satisfied just rule number 1, right? The total number of electrons. Rule number 2 is to place the atom with the greatest valence in the middle. Well, carbon has a valence of 4, so let's draw out the Lewis structures. Carbon, 1, 2, 3, 4. Oxygen with 6 valence electrons, 1, 2, 3, 4, 5, 6. So oxygen has a valence of 2. It has only 2 unpaired sites. Carbon has 4. So carbon goes in the middle. And I'm told to make single bonds to the outer atoms. So I have 3 oxygen atoms, 1, 2, 3. Each of those single bonds represents 2 electrons. So if I'm keeping track of my total, 24, in this case 24 minus 6 gets me down to 18 valence electrons. Rule number 3 now is to add lone pairs to the outer atoms to complete the octet around each of them. So, all right, lone pair around oxygen, it had 2 electrons from the shared. I had 3 lone pairs, that gets it up to 8, and that removes 6 electrons. Now I'm down to 12. I move on to the next one. Lone pair, lone pair, lone pair. That gets 8 electrons around that oxygen and removes 6 of my electrons. I've only got 6 left. Then the last oxygen, lone pair around it. Now I have 2, 4, 6, 8 with the shared pair. That uses all of my electrons up. So now I have finished rule number 3. I've satisfied the octet of all of the outer atoms. Rule 4 is place any remaining electrons around the central atom. But I don't have any remaining electrons. I've used all of them up. There's nothing left. So then I move to rule 5. Make multiple bonds as necessary to complete the octet around all atoms. Well, all of the oxygens have a full octet, but carbon does not. It has only 3 bonds, each bond having 2 electrons. It has no lone pairs, so it has only 6 valence electrons around it. So I need to make a multiple bond. In this case, I'm not going to take one electron from one element and one from the other. I've moved away from that. I've already placed the electrons in either bonds or pairs, so I don't have any unpaired electrons. So what I will do is simply take one of the pairs from one of my oxygen atoms and share the whole pair with carbon. Now, it could be any of the oxygen atoms, and that will come important later when we talk about resonance structures. But for here, I'm just going to use the example from the oxygen on the left. So I'm just going to take a lone pair here, and I will bring that lone pair in and simply share it with carbon. What that gives me then is carbon with a double bond now. Oxygen, we use that lone pair, so there's a lone pair on top, and on this side, oxygen has 8 around it, 2 lone pairs and 2 in bonds, 2 bonds. Each of those have 2, so that's 4 electrons, so 8 total around oxygen. And then we can see that carbon is now satisfied. Carbon now has 4 bonds. Each bond has 2 electrons in it, so carbon now has 8 valence electrons around it. And each of the other oxygens still has 8 valence electrons around it as well. And so we could draw something like this as a valid Lewis structure for CO3 2-. Let's do just a couple more examples quickly. So we have here 3 different molecules. We've got silicon tetrachloride, we've got carbon with 2 hydrogens and an oxygen, and we have C2H2. Let's just start at the top here. First rule is to list the total number of valence electrons. So silicon has 4 valence electrons, and if I draw its symbol, Lewis symbol, 1 around each face, it has a valence of 4. Chlorine, on the other hand, has 7 valence electrons, and there are 4 of them, so I have 28 valence electrons from chlorine. And its Lewis structure looks like this: 2, 3, 4, 5, 6, 7. I have a valence of 1. So silicon goes in the middle, and I make single bonds to all of the other elements, all the outer atoms. If I sum up my total, 28 plus 4 is 32, and then I made 4 single bonds, each of them is 2, so that's 8. So I'm back to 24 electrons. Now I start to put electrons around the outer atoms to satisfy the octet. So it's 1 lone pair, 2 lone pairs, 3 lone pairs around that chlorine. That takes 6, gets us to 18. 3 lone pairs around that top chlorine, that's 6, gets us to 12. 3 lone pairs around this chlorine, that's 6, that gets us to 6. And then 3 lone pairs around this chlorine, that's 6. I have used up all of the electrons. Now I just evaluate. Well, each chlorine has 3 lone pairs, so that's 6, and a bond, that's 8. So each of the chlorines is happy at 8 valence electrons, and silicon has 4 bonds around it. Each of those is 2 electrons, so it has 8 as well. So all of the elements are satisfied in this case. We don't have any other adjustments we need to make, and we've used up all of our electrons, so that's good. Let's move to the second example here. So carbon, we already know, has 4 valence electrons and a valence of 4. Hydrogen has just 1, so there's 2 of them. Oxygen has 6, there's just 1 of it. Carbon has a valence of 4, so it goes in the middle. And then each of the other elements go around it: oxygen, hydrogen, hydrogen. And if I add up my total number of electrons, 4 plus 6 is 10, and 2 is 12. And I will start by completing the octet around all of the outer atoms. Now remember, hydrogen is one of my exceptions. It doesn't need 8 valence electrons, it's happy with only 2. Well, it currently has a bond to each of those hydrogens, which is 2 electrons. So the hydrogens already have the 2 valence electrons that they want, so they're happy. So it's just oxygen that I need to put valence electrons around. And I've already used 6 electrons from the bonds, 3 bonds, 2 electrons in each bond, so that's 6. So I only have 6 electrons left. I put lone pairs around oxygen to satisfy it, and I've used up all of my electrons. But carbon is not happy. Carbon has only 6 valence electrons around it. So I must make a multiple bond by bringing in a lone pair from one of the outer atoms. Clearly, neither of the hydrogens have any extra electrons to make a double bond, but oxygen does, so we can take this lone pair, bring it down to share, and we'll end up with a structure that looks like this, where now carbon has 4 bonds around it, that's 8 electrons, and oxygen still has 8 electrons around it, 2 bonds and 2 lone pairs. And so this would be a valid structure for this compound. Finally, we have C2H2. This one should be a fairly simple structure, but it's a little bit different because we don't have a single central atom anymore. So we've got C2H2, so carbon, each of those has 4, but times 2, that's 8. Hydrogen, each of those just has 1, times 2, that's 2. We have 10 total valence electrons. Now, I don't have a single central atom in this case, because I have 2 atoms, each of which have the same valence, and actually each of which are both identical in identity. So rather than simply placing carbon in the middle and placing the other carbon and hydrogens on the outside, we will simply place carbon in the middle and draw another carbon to it to make both of those be in the middle, quote, and then put 1 hydrogen on each end. And when I look first at that, I can say, well, okay, I've placed the atoms kind of in the middle and the other atoms on the outside. So now I've used up 1, 2, 3 bonds, that's 6 electrons. I only have 4 valence electrons left. Hydrogen is happy, it has only 2 electrons, but each of the carbons is not, they have only 4 electrons. Okay, so if I take those 4 electrons, I have 4 extra electrons, so let's put them around the central atom. So I'll just put 1 lone pair on each of them. And that uses up my remaining 4 electrons, so I have no electrons left, but each of the carbons is still not happy. Each of them has only 6 valence electrons around them. So now I need to look at making multiple bonds. I can only do that by bringing in a lone pair from somewhere, and the only lone pairs I have are on carbon. So if I take this lone pair on the left, bring it in to share it between the 2, I will end up with hydrogen, carbon, and then a double bond. The hydrogens are still happy, but unfortunately, neither of the carbons, only one of the carbons is happy. So the carbon on the left has only 6 valence electrons around it, only 3 bonds. But the carbon on the right is now happy with 8. It has a lone pair and 3 bonds, so it has 8. But the one on the left isn't. So we need to make another multiple bond, and so we bring that other lone pair in to share between the 2. And this will then get us to our final structure, which has carbon with a triple bond, and then single bonds to the hydrogens on the ends. And this then is how we would draw the Lewis structures for these molecules.